Welcome back. This is lesson 3. This is the last lesson of the week. That's a video lesson besides the e-signs that you have to do. So if you haven't already done the exit tickets, the Google Forms for lessons 1 and 2, make sure you go back and do them now before you start on lesson 3, just because I want to make sure you get credit for those lessons. That's how you get credit. You can, if you get it wrong, you can submit again. Try to make sure you get 100 on each of those. That does not mean that if you go through there and take 20 seconds to do it over and over again, I'm going to give you full credit. What I'm saying is, if you take the time to correct your mistakes, then you can get up to 100. And I can tell the difference pretty easily between that and people that are just joking around and trying to get 100 without doing any of the effort. So don't lie to yourself. Don't try and lie to me. I'm going to find out. And remember, grades are due this week. So that's why I'm reminding you one more time. Okay? Right, so the eye. If you don't have the guided notes up for the eye yet, just go ahead and pull them up. It's pretty plain and simple here. What we're going to be talking about are the structures of the eye and the functions that those provide for us. Our eyes are pretty amazing darn things. If we're all lucky enough to be able to say that we have them and we can see with them, it's a wonderful thing. And I've had students that were vision impaired in the past, and it's a hard unit just because of how wonderful it is to be able to have the blessing of having eyes, and describing it all. It's just hard. But lucky enough for us, I think nobody's having that kind of problem this year. So you're not to take out your homework. I changed that. I thought I edited that slide out. We are going to be talking about, first, how does the sun send its energy to Earth? It's important to just remind ourselves of this, because if we don't think about that, then we're going to forget that basically where this light is coming from in the first place. Mind you that the sun produces all of these forms of light. Gamma radiation really gets absorbed before it even leaves the sun's surface, though. Remember, down on this end of the spectrum, it's much more energetic, much more interactive, and it gets to be less and less and less. So some of these forms of light get taken out by our magnetosphere and our atmosphere, and what we end up with most is visible light, right? And inside of that we have the more energetic forms of visible light, like purple and blue, and the least energetic forms of visible light, red and orange. In the ultraviolet spectrum, oh, I hate that bar right now, I'm sure you guys do too, you have more or less problematic forms of UV radiation, and they classify them by the wavelength. UVC is the most damaging, UVA, UVB, all those things can be problematic for you. You also get a fair amount of infrared radiation as well that ends up coming through the atmosphere to us, and that's the heat of the sun that you're feeling. It just much more easily transformed into thermal energy in our skin. So they are all the same thing, right? They're still all light. They're just different frequencies of light based on their wavelength. One more look at this. Violet you can hardly even see, and dark red you can hardly see, because they're just going towards the ends of the spectrum that are hard for our eyes to perceive. And as violet comes through, it is bent the most because it has the shortest wavelength, and red is bent the least. Now, in terms of looking up there at the sky, why is the sky blue? We just said that scattering occurs as well, right? And the things that are going to scatter most often are going to be the more energetic forms of light, which are blue and green and yellow, leaving red and orange and yellow usually to come straight from the sun towards us. Now we get to this picture here, just refreshing us on those interactions and the human eye. Okay, so here's our objective for the day. Distinguish between reflection, refraction, and absorption in order to explain how the human eye works. You kind of need to know those differences and make sure you're understanding those interactions. That's why we reviewed them, in order to understand how the eye works, because the eye makes use of all those interactions. So how does your eye process the light waves it receives? How does it take that light and make it something we can understand? We just want to show you one quick view of a video here of how refraction works. Actually, I usually just have you watch these online. So go take a look at this video right now, pause this video, and go into the slides to take a look at that. So I want you to think, how do you actually see it? This is a stop and jot here, but I really want you to do a stop and think. How do you actually see that light? What allows you to understand what you're seeing right now? Now, I'll give you a hint. It's not like you have a computer processor that you plug into, like a light sensor. You have a brain. It's a pretty amazing process. Somehow in your brain, you're making up all this, what you call light, right? Just like your ears allow you to hear, right? And some animals basically hear with vision. I'm sorry, hear with vision. See with hearing, right? They have such good adept hearing that they almost see what they hear. Like a mole, for instance, which does not have good eyesight, but has such good ear sight, kind of, that it's able to image out where it is. So we'll go one at a time through the structures of a human eye. These are all of them. You don't have to copy them down just yet, even though we're only going to learn a couple of these different things. Who cares about the fovea and the choroid, right? Let's start with the outside. This is the cornea. The cornea is the clear lens in the front. You actually have two lenses in your eyes. This is a fixed, harder lens. It's still squishy, of course. Don't try and squish it, but it's not shape changing. It stays the same shape. Whether that's a shape that's helpful for your eyes or if it's messed up like mine are and you have to wear glasses, this is the first place where light starts to come into your eyes. You notice the shape of it as being curved. This is what you call a convex lens, where the light coming into it is going to start to bend due to, I'm sorry, I'm getting ahead of ourselves, right? We'll just talk about the structure and then we'll talk about the function. So it's a clear lens. It's transparent, meaning the light's able to go through it, and it's fixed. Now the function of it. This allows for the passage of light into the eye, and it also starts to focus it due to refraction. Remember, the shape of it and also the fact that it's more dense than the medium around it is going to start to bend the light, which is good. If light's coming in from up top and you want it to go into the back of your eye, it's going to have to go here and then change direction, right? Or if it's going straight in, it's not such a big deal. But the curvature of your lens and also the fact that it's more dense than the air around it both help to focus light in through your pupil, which is the next one. So your pupil is actually a hole in your eye. It is not an actual black dot that's on your eye, right? It's not a hole in terms of like your eyes leaking, but it is the hole that basically the entry point. It's kind of like a doorway that's circular between your lens here and your eyeball, which is like a big water balloon filled up with fluid. The pupil size is controlled by basically your muscle. So it's not necessarily like a structure, right? It's almost like a lack of structure. It is a hole where light enters in. So right now the cornea, I had a joke about the cornea, but it's pretty corny, right? The light comes through the cornea, refracts in through the pupil, and basically how big or how small that pupil is will decide how much light is coming through. If you were to turn off the lights in your room and look, or go into the bathroom or something like that, or on your phone, right, and go into a sunny area, you'll notice that your pupils constrict, meaning that you have very, very tiny pupils. You don't want to let too much light into your eyes or else you're going to have pain, right? If you ever walked outside on a sunny day after being inside in school, your eyes like hurt for a second. It's because the constriction of your pupils, basically your eyes saying, hey, too much light, dummy, you're going to break our eyes. We're pretty sensitive here, right? So make sure that you wear sunglasses outside. Is one part of how to constrict the amount of light coming into your eye in the first place, but your irises do a pretty good job of that too. So the function of that is just to allow light to enter into the eye. It's a doorway. It is also pretty cool, right? If you ever go to the eye doctor, they might put some drops into your eye to expand your pupil by contracting your muscles in your eye. This is kind of like if you've ever had a cramp in your muscle, it gets like stuck in one spot. Eye doctors will actually give you droplets to cramp up your eye muscles so that it rips your pupil into a bigger hole. Why do they do that? Well, they want to see into the back of your eyeball. That's more to come later, right? So when the eye needs more light, the pupils get larger, allowing more light to enter into the eye. Nocturnal creatures tend to have huge pupils because they have to let in lots of light. And speaking of which, well, I guess I won't go that far just yet. When the eye needs less light to enter, the pupils get smaller. That's like if you were to turn on the lights and turn off the lights and hold your eyes in front of a mirror. Don't hold your eyes, it sounds weird. Just look at your eyes. You'll see how the pupils get bigger or smaller and when they get bigger or smaller. Okay, and that's all controlled by your fancy, beautiful colored muscles called your iris. Irises are also plants that are blooming right now out there in the gardens around your neighborhood, but they are the color muscle that is around your eye. A lot of people think, oh, you got like gems in your eyes or something. Nope, it's a muscle. Take a look. So you actually see the muscle fibers. It's a very unique muscle in your eye in terms of the structure, right? You can actually see the fibers terminating at the end here. And as they contract, they allow the pupil to get bigger, meaning there's more light coming into your eye. And your eyes automatically do this, right? I don't think you force your eyes to do one or the other. But as they constrict, you get to see more of the muscle. Now, you're usually not that close up to it, otherwise you'd be freaked out. But, you know, they look blue, red, I don't even know the colors of eyes, honestly. Let's take a look at some of the other pupils and irises in the animal kingdom, though. This is not a human being, this is a frog. Notice that it has a slit pupil this way, a vertically slit pupil, and a very weird iris. And each of these animals, usually it helps them to identify prey or their predators more easily. This kind of a pupil comes from a cuttlefish, which happen to be really deep sea creatures which have fantastic everything. They are amazing creatures. If you ever want to waste 15 minutes, go watch cuttlefish videos about how awesome they are. This comes from a goat. It's got kind of like that hexish pupil and iris. So the function of the iris, once again, is to control the amount of light entering the eye through the pupil. It basically determines the pupil size. Next we have the sclera. The sclera is the white part of the eye. This is basically, if you're thinking about your eye as a water balloon, this would be the latex of the balloon itself. It is a place where the muscles that attach to your eye can attach to. Yes, you have muscles attaching to the back of your eyeballs. Otherwise, how would you be able to move your eyes around, right? Looking up and down this way and that way. It is also white. It doesn't have to be white, but it is just basically there for attachment and to keep everything in place. It's kind of like your skin, right? It's made of a skin-like tissue that covers all the eyeball except the cornea, and it contains the fluid of your eyeball, the squishiness. So that's the function of it. It supports the eyeball and provides attachment for muscles. Go ahead and look up and down and left and right. You can actually feel where those muscles are attached to your sclera. Kind of freaky. Okay, here comes the cool part to me, is the lens. The lens is the second lens of your eye. Why they had two lenses and they named one of them lens is beyond me, but there you have it. This is what we call the lens of the eye. This is a converging lens, so this allows us to see objects that are near and far. In other words, it can change shape. It is squishy, unlike the cornea, which is a fixed shape. So because of that different shape and the refraction, once again, it will change how much or how little the light will refract and the angle of refraction once it leaves that surface. If you were to look far away, you have what's called a shallow depth of field. If you're looking far away, everything close to you gets fuzzy, right? And if you look close, everything else gets fuzzy far away. And what happened in that meantime is that your lens has adjusted. It squished more or squished less to change the angle of light coming through it onto your retina in the back of your eye. Pretty cool stuff. You know, if you sit at a computer all day and you constantly look at something 2 feet from your face, your lens gets to be atrophied. It does not work as well, and it will not help you when it comes time to actually focusing outside of that. That is not most of the reason why people need glasses, but it certainly can damage your eyesight in terms of your ability to see on a good day. It makes you have lazy eyes. Alright, so I'm going to stop the video here and then we'll continue in the next video.